Okay, so shall we start? Today is April 2nd, and it is our third Zoom discussion. So today we're going to talk about limits of functions. So first, let's review the definition of a cluster point. So the definition, let A be a subset of R, a point C in R is a cluster point of A if for every delta greater than 0, there exists at least one point x in A with x not equal to c such that x minus c absolute value is less than delta. Okay, so we all know that's the definition of cluster point. So use this definition. Can we prove the following? So let's call this a theorem. A number C in R is a cluster point of a subset A of R if and only if there exists a sequence AN in A such that limit of AN is equal to C and AN is not equal to C for all N in N. Okay, so how do we prove this? Let me write over here. Proof so if C is a cluster point of A, then for any N in N, the 1 over N neighborhood so let me denote it as V sub 1 over N C. So this is a neighborhood centered at C with radius 1 over N. Okay, so that by definition contains at least one point AN in A distinct from C. Okay, so then AN in A and AN is not in C, and the difference between AN and C is less than 1 over N because AN is inside this neighborhood. So that implies, because as n goes to infinity, that goes to 0, so that implies limit of AN is equal to C. So, because this theorem is an if and only if, so we have to prove the other direction. Okay, so we show that if C is a cluster point, then we can find such a sequence. Now, conversely, if we have such a sequence, we want to show that C is a cluster point. Okay, so conversely, if there exists a sequence AN in A but not equal to C with limit of AN is equal to C, then for any delta greater than 0, there exists a k such that if n is greater than k, we have an minus c is less than delta, right? So that implies an is in a delta neighborhood of c. Okay. So therefore, this neighborhood is non-empty, right? So other than the point C, it also contains the point AN. All right, so that satisfies the definition of a cluster point. Okay. So that's just some review, and now we're gonna introduce the definition of the limit. So definition. Let A be a subset of R, and let C be a cluster point of A for a function f from A to R, a real number L is said to be a limit of f at C if given any epsilon greater than 0, there exists a delta greater than 0 such that if x in A and 0 less than x minus c less than delta, then fx minus L is less than epsilon. Okay, so some remarks. So usually this delta depends on the epsilon. Okay, so delta usually depends on epsilon. Okay, so this x minus c absolute value greater than 0 is the same as saying x is not equal to c. Okay, so this definition you can write it as L is equal to limit as x goes to c f of x. We can also say f of x approaches L as x approaches c. Okay, so f of x goes to L as x goes to c. Okay, so if the limit of f at c does not exist, so if the limit of f at c does not exist, we say that f diverges at c. Okay. All right. So that's the definition of limit of functions. I'm sure you are all familiar with this. So next, a simple exercise or a theorem. The theorem says that the limit is unique. So if f is a function that goes from A to R, and if C is a cluster point of A, then f can only have one limit at C. So how do we prove that? So if you have good intuition, then you know for uniqueness proof, we assume we have two limits, right? L and L prime. So these are the two limits. And then we want to show that the difference between L and L prime is equal to 0, right? So that says L and L prime are the same thing. Okay, so we do that by using triangles inequality. Okay, so for any epsilon greater than 0, there exists a delta, and we emphasize that this delta depends on epsilon. So let me just write delta of epsilon over 2 greater than 0, such that if x is in A and 0 less than x minus c less than delta epsilon over 2, then f of x minus L is less than epsilon over 2. Okay, such delta exists by definition of limit. Okay, and then also there exists a delta prime of epsilon over 2 such that if x is in A and 0 less than x minus c less than delta prime epsilon over 2, then f of x minus L prime is less than epsilon over 2. Okay? And then what do we do next? Then we take delta to be the minimum of the two. Then, if 0 less than x minus c less than delta, so that implies if it's less than delta and delta is the minimum of the two, that means that x minus c absolute value is less than both of them, right? So then, by the triangle inequality, so L minus L prime is less than L minus f of x plus f of x minus L prime, right? So because x minus c is less than delta, so that means it's less than delta of epsilon over 2, then we have L minus f of x is less than epsilon over 2. So similarly, this is also less than epsilon over 2. So we add them together, you have epsilon. So L minus L prime is less than epsilon, but epsilon is arbitrary. So that shows the difference between L and L prime is 0. So L is equal to L prime. Okay. All right. So of course, this definition, we only restricted our attention on R, and this definition works equally well for any other metric space. So this does not have to be R, it can be any metric space, and this metric doesn't have to be the absolute value, it can be replaced by any other metric. So graphically, so here is a more intuitive graph. So say this is our function, okay? Say this point, let's call it C. So this is our cluster point. Okay, so this is f of x, all right? Let's say this point on the y-axis is L, and we claim that limit as x goes to c, f of x is equal to L. And why is that? Because you take any interval around L of radius epsilon, so this is L plus epsilon, this is L minus epsilon, then you need to find a delta such that if x and c are close enough, meaning the distance between x and c is less than delta, we have f of x minus L is less than epsilon. So in this graph, you can see that if your x is in this interval, then the difference between f of x and L is less than epsilon, right? So we take, say, this interval, right? We make sure it's symmetric. So this is delta, this is delta, okay? So if x is in this interval, then you know the difference between f of x and L is less than epsilon. And also from this graph, you can see that this delta will depend on epsilon, because if I choose a smaller epsilon, right, then my interval here will also get smaller. Okay. All right. Okay, so now let's show a few examples on how the definition of limit is applied. So example A, sort of a trivial example. We claim that the limit of b as x goes to c is equal to b. Okay, so b is a constant here. Okay, so more explicitly, you can say f of x is the constant function b. Okay, then limit as x goes to c, f of x is equal to b. Okay. All right, so given any epsilon greater than 0, so we have to pick our delta, right? So in this case, because it's a constant function, any delta would work. Okay, so any positive delta would work. So let's just pick delta is equal to 1. Okay, this is entirely arbitrary. You can take delta to be your favorite positive real number. Okay, so let delta is equal to 1, then if 0 is less than x minus c is less than 1, we have f of x minus b. So remember, f of x is the constant function b. That's b minus b is equal to 0, which is, of course, less than epsilon. Okay, so by definition of the limit, because such delta exists, we know that the limit is equal to b. Okay, so next, a slightly less trivial example. Let's show limit as x goes to c, x is equal to c. Okay, so we let g of x be x. Okay, so if epsilon greater than 0, so take any epsilon greater than 0, we take, we let delta equals to epsilon, then if 0 less than x minus c less than delta, we have g of x minus c is equal to x minus c, right? X minus c is less than delta, and delta is equal to epsilon. Okay? So for every epsilon such a delta exists, we conclude by definition, limit as x goes to c, x is equal to c. Okay, so both of these two examples are rather trivial. So next, let me show you some slightly more complicated example. Okay, so limit as x goes to c, x squared is equal to c squared. Okay, so how do we show that? Use the definition. So we can let h of x equals to x squared. Then what do we want? We want to make h of x minus c squared, which is x squared minus c squared, less than epsilon by taking x sufficiently close to c. So to do so, we first observe that x squared minus c squared is equal to x plus c times x minus c. Okay? All right, so moreover, if x minus c absolute value is less than 1, then x less than absolute value of c plus 1, okay? So that x plus c absolute value is less than x plus c is less than 2c plus 1. Okay, so here's the triangle inequality, and this we used the fact here. Okay, so if we focus on the part that x minus c absolute value is less than 1, then this is correct. Okay, so therefore, if x minus c absolute value is less than 1, we have x squared minus c squared is equal to x plus c times x minus c. That's less than 2c plus 1 times x minus c, right? So we want this to be less than epsilon. So this would be true if x minus c absolute value is less than epsilon over 2c plus 1. Okay? So as long as this is less than this number, then we have x squared minus c squared is less than epsilon. But this, for this to hold, another important condition is we must have x minus c absolute value is less than 1. So how do we choose our delta to ensure that x minus c is less than this and x minus c is less than 1? So here's the trick. We pick delta to be the infimum or the minimum of the two. Okay, then if x minus c is less than delta, then that implies x minus c is less than 1 and x minus c is less than epsilon over 2c plus 1. Okay, so both the conditions are satisfied, then we must have, by earlier computation, x squared minus c squared is less than epsilon. Okay, so that concludes the proof. Okay, so it is a little complicated, so let's go over this idea one more time. So the key idea is that we restrict our attention on this interval. Okay, and under this condition, we have if x minus c absolute value is less than epsilon over 2c plus 1, we have the difference of the two is less than epsilon. Okay, so you might ask, how do we come up with this condition? So here is why. Okay, so say you want x squared minus c squared to be less than epsilon. Okay, so as before, we factorize. So this will be true. So these are if and only if. And then this is if and only if x plus c is less than epsilon over x plus c, right? And, well, sorry, this is x minus c. And then you might ask, why don't we let this to be delta? We cannot do that because delta only depends on epsilon. Okay, so here this expression, we have x here. Okay, and x is a variable. C is fine because C is a constant number, but here x is a variable. Okay, so that's not allowed. But if we restrict our attention on this, then we can bound the denominator. Okay, so as we saw before, if x minus c is less than 1, then this is less than epsilon over x plus c. Okay? So if x minus c is less than this, then x squared minus c squared is less than epsilon. So this, we use that to get rid of this dependence on x. Okay, so I hope this explanation is clear. So let's see another similar example. So let's show limit as x goes to c, 1 over x is equal to 1 over c. So here we assume c is greater than 0. Okay, c is less than 0. The procedure is almost the same. Okay, so we let phi of x to be 1 over x. Okay, so we want to show limit as x goes to c, phi of x is equal to 1 over c. So that is to say, we want to make the difference smaller than epsilon, right? So when is this less than epsilon? So 1 over x minus 1 over c is equal to 1 over cx times c minus x, right? So this is 1 over cx times x minus c. Okay? So this will be true. So let me write over here. So if we want this to be less than epsilon, so if x minus c absolute value is less than epsilon times cx, then we are fine, right? But again, the same problem arises. If we take this to be our delta, then delta would depend on x, and that's bad. So we want to get rid of this x. Okay? So we want to find a lower bound of this. Okay? So we want to restrict our attention on certain interval. Okay, so if x minus c is less than 1 over 2c, so say here is c, okay, that's 0. So x on this interval. So I pick this to be 1 over 2. This is also arbitrary. Any number less than 1 would work. If something is greater than 1, it will not work because then this interval will include 0, right? Then here this x could possibly be 0. So you would have this is less than 0, which is clearly not possible. So you want to pick a number that is less than 1, so avoid crossing 0. Okay, so if x minus c is less than 1/2 c, then that implies x is between 1/2 c and 3 over 2 c. Okay, so 1 over cx would be less than 2 over c squared. Okay, so therefore, phi x minus 1 over c, which is 1 over x minus 1 over c, now I'm going to replace this by 2 over c squared. So this is going to be less than 2 over c squared x minus c, right? So then how do you make sure this is less than epsilon? Well, you just need x minus c to be less than 1/2 c squared epsilon. Okay, so how we choose our delta? You choose your delta to be the minimum of 1 over 2 c squared epsilon and 1 over 2c. Okay, then if x minus c is then delta, both of the conditions are satisfied. And from the previous computation, we see this is less than epsilon. So we are done. Okay. All right. So I hope this makes sense to you. So another example. So limit as x goes to 2, x cubed minus 4 over x squared plus 1 is equal to 4 over 5. Okay, so we want x cubed minus 4 over x squared plus 1 minus 4 over 5. We want this to be less than epsilon. Okay, so you can simplify this. Okay, here I'm just combining the two terms and nothing special, no tricks involved. So here, what do we do now? So here we have this. Oh, sorry, this I believe should be a 2. Okay. So here I'm simply factoring out x minus 2 from the numerator. Okay, so we want this to be less than epsilon. Okay, you can simply let x minus 2 less than epsilon over this whole thing. But again, this thing here depends on x. Okay, so how do we get rid of that? Again, we can focus our attention on a certain interval. So suppose x minus 2 is less than 1, let's say, then that implies 1 is less than x is less than 3. So if x is on this interval, on 1, 3, then the numerator would be less than or equal to 5 times 3 squared plus 6 times 3 plus 12 equals to 75, right? And the denominator would be greater than 5 times 1 plus 1 equals to 10, right? So this whole thing on this interval, this would be less than or equal to 75 over 10 because we are letting this numerator to be as big as possible and letting this denominator as small as possible. So this whole thing is less than this. Okay, so x cubed minus 4 over x squared plus 1 minus 4 over 5. This is less than or equal to 75 over 10 times x minus 2, right? So that's 15 over 2 times x minus 2. So we want this to be less than epsilon. we just need x minus 2 to be less than 2 over 15 epsilon. So same trick as before, we can choose delta to be the minimum of 1 and 2 over 15 epsilon. Okay, so that delta would work. Okay, so next we talk about sequential criterion for limit. So what does it say? We state that as a theorem. Let f from a to r a function, and let C be a cluster point of A, then the following are equivalent. Okay, if someone knows how to get rid of that, please leave a comment, let me know, because this thing pops up all the time. It's kind of annoying. Tomorrow. Okay. So the following are equivalent. 1, limit of f of x as x goes to c is equal to L. 2, for every sequence xn in A that converges to C such that xn not equal to C for all n in n, the sequence fxn converges to L. Okay, so we are not going to prove it here because I think it's a relatively it's relatively intuitive. So here is your sequence xn. Okay, so your xn goes to something, and then if you apply your f on this set, then the f is also going to converge. Okay, so intuitively speaking, if xn minus c is small, say less than delta, right, then that implies f of xn and L is also small. Okay, so that's a criterion for convergence. So we have a similar criterion for divergence. So let me state it. Divergence criteria. So let A be a subset of R and C in R be a cluster point of A, then A, if L is in R, then F does not have limit L at C if and only if there exists a sequence xn in A with xn not equal to C for all n in n, such that the sequence xn goes to C, but f of xn does not go to L. So if a sequence goes to C, but f of that sequence does not go to L, then f does not have limit L at the point C. Okay, I think it's rather intuitive. B, if L is in R, then F does not have limit L at C if and only if there exists sequence such that with xn not equal to c for all n, such that xn goes to c, but f of xn does not converge. Okay, so that's the only difference. Everything else are the same. So for part A, or for the first statement, it can possibly converge, but does not converge to L. And for B, it just does not converge. Okay, in both cases, F does not have limit L. Okay, so either it converges to a number different than L, or it does not converge at all. Okay, so example. Okay, so example. Limit as x goes to 0, 1 over x does not exist in R. Okay, so how do we do that? Well, okay, so let xn be the sequence 1 over n, so x1 is equal to 1, x2 is equal to 1 over 2, x3 is equal to 1 over 3, etc. So then xn goes to 0, right? But 1 over xn, that equals to n, right? So that does not converge. So limit as n goes to infinity, 1 over xn does not exist. Okay, so we have xn goes to 0, but 1 over xn does not. So we know this 1 over x, the limit does not exist. Okay, so another example, limit as x goes to 0, sine x does not exist. So sine of x just means the sine of x. So if x is positive, say 1, it is 1. If x is negative, say negative 0.1, it is minus 1. Okay, so sine of x is equal to 1 if x is greater than 0. It's equal to 0 if x is equal to 0. It's minus 1 if x is less than 0. So alternatively, for x not equal to 0, sine x is equal to x over absolute value of x. Okay, so we're going to show the limit does not exist at 0. Okay, so how do we do that? So here's the idea. We want to construct a sequence xn such that xn goes to 0, but sine of xn does not converge. Okay, so we can take xn to be minus 1 to the n. Okay, so graphically this is 0, so we start at minus 1 and then 1 over 2, minus 1 over 3, 1 over 4. Okay, so it's jumping left and right around the origin. So sine of xn is simply minus 1 to the n, right? So as you can see, this sequence does not converge. Therefore, the limit does not exist. Okay. So next example, we want to show limit as x goes to 0, sine 1 over x does not exist in R. So graphically, what does it look like? So around 0, it changes real quick. Okay, so that's roughly the graph of that. So as you can see, around 0, it's changing too fast. So intuitively speaking, limit does not exist. But how do we show that? So how do we show that rigorously? So here's the idea. So we want to construct two sequences, say xn and yn, both converge to 0, but sine of 1 over xn and sine of 1 over yn, so the limit of these two are not the same. If the limit exists, since both xn and yn goes to 0, that means xn and yn, they are very close. So if limit exists, then both of these two limit has to agree. Okay? All right. Okay, so how do we construct such sequence? So let's recall that sine of t is equal to 0 if t is a multiple of pi. Okay? And sine of t is equal to 1 if t is equal to 1 over pi plus 2 pi n, right? So the idea is we let x be 1 over n pi, then limit of xn is equal to 0, and g of xn by construction is equal to 0. Okay, so the limit of a bunch of zeros is of course 0. But on the other hand, we let yn to be the inverse of 1 over 2 pi plus 2 pi n. So again, yn goes to 0, and g of yn, as we know from here, it is equal to 1. So limit of gyn is just the limit of the constant sequence 1, so that is equal to 1. So as you can see, these two are different. So that shows the limit of sine 1 over x does not exist. Okay, so next I'm going to show you some limit theorems. So first, the definition. Let A be a subset of R, and let F be a function from A to R, and let C be a cluster point of A. We say that F is bounded on a neighborhood of C if there exists a delta neighborhood so V sub delta of C, and a constant m greater than 0 such that the absolute value of f is bounded by m for all x in A intersecting V delta of c. Okay, so that's the definition, which is fairly intuitive. Okay, just as what you would expect. So next theorem, if A is in R and F goes from A to R, has a limit at C, then F is bounded on some neighborhood of C. Okay, so how do we prove that? The first intuitive idea. So if F has a limit at C, right? So say the limit is L. Then as long as your X is close to C, F is close to L, right? So L is a fixed number. So if it's close to L, then it's sort of not far from L, so it's bounded. Okay, so proof. If L is the limit of F at C, then say for epsilon equals to 1, there exists a delta greater than 0, such that if 0 is less than x minus c is less than delta, then f of x minus L is less than 1, right? So the difference between f of x and L is less than or equal to fx minus L, which is less than 1. So that implies the absolute value of f of x is less than the absolute value of L plus 1. So this is a fixed number, right? So this is bounded, provided that x is close to c. Okay. All right. So what if C is not in A? Then take M to be L plus 1. If C is in A, then we can take M to be the supremum of f of C and L plus 1. Okay? Alright, so you might wonder, why do we have to distinguish the two cases? So here is the explanation. Say this is your function, right? Say C, if C is in your domain, okay, you take your epsilon to be 1, so this L plus 1, this is L minus 1, right? So as long as, say, you're close to C, then your difference, your function value cannot be too far away from L. In fact, it's between L minus 1 and L plus 1, so it's bounded. So that's the case when C is in your domain. So the case when C is not in your domain, so here it's there, but at C, okay, it's somewhere here. Okay? So again, if x is close to C, say here, that's L plus 1, L minus 1, right? So everything here has been taken care of except at C. Okay, in this case, say C, this is f of C, right? So we can take M to be the supremum or the maximum. It doesn't matter because there are only finitely many points. Say L plus 1 and fc. Then everything in this interval, including C, is less than M. Okay. So that's that. Okay, and then next some theorems. some limiting theorems, which is not very surprising, totally expected theorems. So let A be a subset of R, and let F and G be functions on A to R, and let C in R be a cluster point of A, and let B in R, so 1 or A. So let's say limit as x goes to C of F is equal to L, and limit as x goes to C of G is equal to M. Then limit of F plus G is equal to L plus M. Limit as x goes to C, F minus G is L minus M. And limit as x goes to C, F times G is equal to L times M. And to limit as x goes to C, BF, so B is a constant, that's equal to B times L. Okay, totally expected. And part B, so if H is a function goes from A to R, and H of x is not equal to 0 for all x in A, and limit as x goes to C of H is equal to big H, which is not equal to 0, then limit as x goes to C, F over H is equal to L over H. Okay, so that's totally expected. Okay, so given that, we can solve a lot of problems. So here are some examples. So limit as x goes to C 1 over x is just 1 over limit as x goes to C x. C with 1 over C provided that C is not equal to 0. Right? That's part B of the previous theorem. Also say limit as x goes to 2 x plus 1 times x cubed minus 4. So you can write this as, so it's the limit of product, so that's the product of the limit, provided that the limit of both exists. In this case, since they're both polynomials, we know they exist. So you plug in 2, you have 5. Here you plug in x is equal to 2, you have 4. So the limit is 20. Okay. Another example, limit of a rational function. So this would be limit as x goes to 2, x cubed minus 4 over limit as x goes to 2, x squared plus 1. So provided that the limit of your denominator is not equal to 0. In this case, it is not. So that's just 4 over 5. Okay. All right. So next, limit as x goes to 2, x squared minus 4 over 3x minus 6. How about that? So it's tempting to do this. Sorry, this square. No. Limit x squared minus 4 over limit 3x minus 6. So it's tempting to do that, but this is not allowed because if you plug in 2, your denominator is equal to 0. Okay, so the theorem really does not apply. So what do? So this x squared minus 4, 3x minus 6. So you can factor your numerator as x minus 2 times x plus 2. And your denominator, you can take out the 3 and write it as 3 times x minus 2. So these two cancel. Now you don't have this dividing by 0 problem, and then you just plug in x equal to 3. So, sorry, x equal to 2. Then that's going to give you 4 over 3. Okay. All right. So in general, limit as x goes to c, p of x, q of x is equal to p of c, q of c, provided that q of c not equal to 0, and this is true for any polynomial, pc and qc. Okay, so this is a special case. Well, this is not a special case, but this is a special case. After canceling out the singularity, that becomes this. Okay, so that's that for today. I hope you learned something, and if you have any questions, leave a comment or send me an email. All right, see you next time.